Hello and welcome back, everybody. We are looking at the top of page 140 in the workbook, and this example that we're about to look at is our first example of calculating the divergence of a vector field. We're going to do that and then also talk a little bit about the significance of that calculation that we do. All right, so we are given a vector field that looks like x squared I plus yj plus zk. And the first thing they'd like us to do in part A is to calculate the divergence of that field at a point. So why don't we start by reminding ourselves of what the coordinate definition of divergence was. Okay, I'm just going to write out that formula. This comes from the previous page. Partial z. Okay, remember that f1, f2, and f3, those were just the names of the three components of our vector field. So f1 would be x squared, f2 would be y, and f3 would be z. So we need to take three partial derivatives here. Let's see if we can break that down. So partial f1 partial x, we're going to take this x squared, take its derivative with respect to x. Okay, then we move over to the y. Its derivative with respect to y is 1. And then finally z, its derivative with respect to z is 1. And so what we end up with is 2x plus 2. Okay, there's our formula for the divergence. Okay, and they wanted the divergence at a specific point, 0, 0, 0. So to finish this, we just need to substitute those coordinates in. Okay, so the divergence of f at 0, 0, 0. X, y, and z are all 0, and our formula just has an x in it, so all we really need to do is to substitute x equals 0 in. Okay, and we get the number 2. And notice, just want to emphasize that that's a scalar that we got. Okay, the divergence is a scalar quantity, and the fact that that number is 2 tells us that we've got net outflow out of the point 0, 0, 0 in this vector field. Okay, so we're done with the calculation part of this. What about the interpretation part of it? Okay, so part B asks us to give a practical interpretation of the product divergence of f at 0, 0, 0 times delta v, okay, where delta v is a cube centered at the point 0, 0, 0. Okay, well, we can figure out kind of logically what that has to mean just by examining units here. All right, so let's start by just writing down the expression that we're trying to analyze here. Okay, we'll look at this one piece at a time, starting with the divergence. Okay, well, what was the divergence of a vector field again? Well, it was basically outflow per unit volume. It was a flux density. So if we wrote that out in words, it would look like this: outflow per unit volume at 0, 0, 0. And delta V is the volume of a small cube that we're putting around 0, 0, 0. So what happens if you multiply those expressions times each other? Okay, well, the volumes cancel, and what we're left with is just outflow. Okay, so we can look at this and say that this must measure flow, this product that we took. Okay, if we want to put this maybe into one statement, I'm just going to write a brief sentence to kind of tie all this together. So this product of the divergence times delta V measures the approximate flow of the vector field F out of the small cube. You might think about why we say approximate, why this is an approximation and not an exact flow. Okay, and we're done with the problem.